John Carrier from Cray is next. He's going to talk about the HPCS workloads. John Carrier.
It worked yesterday.
Trying to find some energy.
Yeah, get it up there. Okay, so I'll try to make this quick, or I hope to. There's a bunch of slides to run through. It's mostly what I want to do today is introduce what these HPCS scenarios are. We've been talking about them for a number of years as part of our program with DARPA. I've been talking about them within the new benchmarking working group. That's the word thing. So I'm trying to get there, and so I just want to give some context, background to everybody so you can see what these things are and what Cray has done with them and why we've mentioned that they might be something of use to the benchmarking work group. So to start out, I want to quote the author of the DARPA's HPCS I scenarios, we were talking yesterday morning following the benchmarking meeting on Sunday, and his response to this is like people talking about performance monitoring tools of I/O and actual I/O benchmarking is like comparing apples with flying pigs. And so to that I credit our dear Henry Newman. Based on that, that's who wrote the scenarios. We're all set. So what are the scenarios exactly? Well, DARPA has a program called the High Productivity Computing Systems, and part of that, they're focusing mostly on the mainframe, interconnect network, processors, things to make the user community more productive. Very little talk about I/O, very few requirements in I/O, but what they did is they wanted to focus on I/O scalability, and so they gave us a set of workloads, 14 scalable workloads that they published, and the first version came out I think 3 years ago, and then they were given to us as something that we had to demonstrate on our DARPA platforms. Now the point is that these are descriptions of workloads. They are not benchmarks themselves, and so there's well-defined rules of what they wanted us to execute in order to demonstrate the scalability of the solution that we gave them. They really wanted us to get away from giving them a single number. We've had talks about single IOR numbers. That's of no interest to most of these customers, what we call the HPCS mission partners, who are looking at large-scale systems. So the idea then is that when you're done with these things and you've demonstrated on a small scale how your system scales by ramping up the number of scalable units or bases of your file system, that they could then extrapolate that to what they should see as for expected workloads using their real jobs. So first off, within this, there's two concepts of environments, and there's different mission partners have different focuses. There's some groups in DARPA that are focused on streaming I/O. They're looking at I/O capture. So this is looking at data that's streaming through an I/O node or streaming into a node. It's being processed and then written out to storage. And then there's the more typical parallel I/O workloads that we're used to with Lustre, where you have multiple threads, multiple compute nodes all talking to a shared file system. And so we have these two environments that are splitting it up. Now when you look at the actual scenarios, there are 14 of them. The first 4 of them are dedicated to the capture environment. They're looking at how do you do streaming I/O. The remaining 10 are focused on typical parallel I/O solutions. And so Lustre, clearly I want to focus everybody's attention when they look at this document. The first 4 are important. There are customers of Lustre, customers of file systems that do have capture I/O requirements. My message to Cray's partners over the years has been we understand Lustre does better for the parallel environments, but we can't ignore the fact that there are people out there that are looking for capture. But for today, I'm just going to focus on the parallel, okay? So within these, the parallel workloads, there are four variables that we're changing around. One of them is the access method, whether it's a shared file or with end-to-one I/O access pattern or the file per process. The I/O size, we're looking at large blocks with 1 megabyte to 10 megabytes in I/O, and this would be something that you'd see with shared file as a segmented I/O pattern, or smaller being something below in the tens to hundreds of kilobytes, and this would be something that would lead to like a strided I/O pattern for shared files. There's also whether the file access pattern is sequential or random, and then very clearly metadata operations are important. If I focus just on the checkpoint restart scenarios, these are scenarios 5 through 8, and just showing you how these 4 scenarios are representing these workload definitions they've given us are varying the record size, whether it's a large or small, and then also the access pattern, where it's shared or filed per process. For all of these, the way they wanted us to test these with the description, the detailed description of the workload, is they want you to run the workload, and then they want you to do it on multiple size file systems. So at first you take a file system of a certain size, you double the components, you measure it again, you double the components again, you end up with 3 numbers. You can then define the scalability of your file system or your solution. And within this, we are clearly expecting to see bad performance. It's meant to give real life workloads, show where you shine, show also where you fail. It's not to hide it behind a single number. If I focus on the shared file scenarios, just to give an idea of what we're looking at, is that on the left, your left, it's the scenario 5. This is for what's called a large shared I/O. It's a segmented I/O pattern. So within a single shared file, there are a number of processes, and each process is given its section of the file to write into. That's in contrast with a small I/O for the shared file, where you're writing the data out by each array, and within each array, every one of the processing units has got its own little section of that array that it writes. And so the description, the detailed description they give us, which is shorthand there below the diagram, is just, there's the description of what they wanted us to do. This is sort of the overlap, the diagram of how they're doing this, just as an example, okay? More details like this are in the actual document. But then we come to the document, and the document doesn't have, it's just a description of the test. There aren't any actual tests themselves. They're just describing the workloads. So there had been over the years, the HPCS mission partners had come up with a number of implementations of these, but none of them were open to the public. They've been given to, they were using them internally, but they weren't sharing them. So Cray took it on finally at the very last minute and did our own. And we've published those now under Cray's BSD style open source license and put them up on SourceForge. The URL is there. You can also just get to it by going to SourceForge. The scenarios themselves and our implementation are completely file system agnostic. There is nothing Lustre specific in the descriptions, and our repository also includes scripts that demonstrate our use of them, how we've been playing with them, but there's a number of parameters that you can change on the command line. What we did last year is we tested them. We came up with our first implementation of this last winter. In December 2010, January 2011, and then we needed a place to test them. So as we had this great opportunity when Oak Ridge National Labs was decommissioning Jaguar XT4, they had on that system 18 DDN 9550s, and then that system was using 72 Lustre OSSs. The opportunity of having that much I/O to play with was terrific, because we got to completely reconfigure the storage. We didn't rewire anything, but we got to reformat the file systems to meet our needs. And the way we did that, well, before I get there, is that when you look at those data arrays, they're actually not, you're looking at Lustre. In Lustre, we tend to look at the number of Lustre OSSs and the number of arrays that are behind that. And so typically, you're focusing on the number of a ratio of OSSs to servers. Oak Ridge had actually wired these up so that the 2 racks of arrays were being shared amongst 8 OSSs. So in the context there, the scalable unit is actually 8 OSSs and 2 arrays. Okay? And what we're going to do is we're going to double the number of SSUs between subsequent tests. So we had 18 of these arrays to play with, which would be a total of 9 SSUs, and we consumed 7 of them for the test. So here's what we did for file system definitions. We had FS1, which is one of those SSUs, 8 OSSs, and then 2 racks, and then on down for the 4, for the 3 definitions. So we had 1, 2, and 4 SSUs. By the way, I've got bifocals, and it's just confusing the heck out of me every time I look down here, because it goes in and out of focus with the screen in front. So you probably didn't notice that, but it's driving me crazy. Anyway, and clearly this is a system that had 8,000 compute nodes. We had plenty of resource to drive the I/O. We had way more than we needed. So what we wanted to do first off is scale the I/O with our scenarios to see how many actual clients we needed per OSS in order to get a good number, and then we were going to use that for the rest of the tests. So in this slide, we're looking at the scalability. We've got the 3 the three the three file systems. So the red is file system 1, green and the triangles is file system 2, and red and the blue and the circles is file system 4. We scaled them up for different numbers of clients, and then I've circled there where we saw the numbers plateau, and that turns out to be about 4 clients per OST in the system. And so we use that ratio then for the rest of the test, just to simplify it. We weren't having to drive thousands of clients. We could actually maximize the bandwidth through the storage arrays by just using 4 OSSs, 4 clients per OST. So here are some of the results. I'm going to don't want to belabor them. The first one is just with the large I/O, so I'm going to go large I/O, show with sequential I/O, random I/O, and then metadata performance. So for the sequential I/O, we've got scenario 5, which is an N-to-1 shared file access method, and then scenario 7, which is file per process. And you can see they scale. It's not linear scaling, but we definitely see that the file per process is scaling better than the shared file, and that we see write performance is not quite as good as the read performance. When we compare this with random I/O, it's flat. So in this context, we were thrashing the file system. The demonstration was that for the parameters we were using on this, which I'm not trying to go into details here, but we were just able to make the performance really bad. In fact, if you go back to this previous slide, we're getting fairly good. We're expecting to get 5 megabytes per second or 5 gigabytes per second out of every one of the out of the SSUs, and it scales pretty clearly. Here we're getting 2 megabytes per SSU, so we really throttled it. We didn't have the time to investigate what we were doing differently and what we could have done to give better parameters to give the performance, because we were doing this as they were trying to pull the plug on the system. Metadata performance, they wanted us to repeat the test with cold cache and warm cache. And so cold cache is where there's ideally the way they described it was to start it off, to restart the file system. We didn't actually do that. We came up with another way of dirtying the cache to make the thing work. But because Lustre has a single metadata server per file system, the fact that we had these 3 very different size file systems with different numbers of OSSs, the fact that each one of them only had a single MDS, we didn't expect to see anything different. We didn't expect to see any difference in performance between those, and we actually didn't. So the next thing, lessons learned. So at the end of this day, we had 5 days, and we were basically working around the clock trying to get these tests run, going through different hardware failures and different configurations on it before, again, as they're decommissioning it, getting ready to pull the plug. We found out that one of the problems we ran into is that the scenarios describe things in terms of data size. They want you to take 10 times the total amount of memory in the system or in the data path, and then write that size file. And if you do that, especially, for example, on those random I/O tests, you will never complete. And so what we've ended up being forced to do is we reanalyzed the data looking at the time series of where the data was, and we saw very quickly that we get to a steady state. And based on that, we went and talked to DARPA, and we changed our tests so that we could actually give a time at which the test would end, so that you could actually have a scheduled amount of time and know you'd run the test and be complete in the right, before your allotted time ended. The next thing was creating a cold cache for the metadata test. So the way the tests were described is they wanted you to actually restart the whole file system. Well, on something like Jaguar, you can't restart the whole file system. You got to restart the whole machine. It just doesn't make good use of your time, and it's definitely not a good use of the resource. And what we found was that if we made multiple copies of the directory trees, and then for each one of the different test cycles that we wanted to run, you could actually then, every time you went to the new directory tree, it was a totally clean cache. There was no reference to that structure in memory anywhere, and it acted actually quite very similar to as if it was a cold cache. So we did do the reboot and test, and then we did this other mechanism of looking at different directory trees, and the results were essentially the same. The final version of the DARPA document that's out on our SourceForge site includes the notes that we made on these results here. It also includes diagrams that we changed, the actual change to the data path flow to match what we've implemented. Okay? So finally, the conclusions is, I just want to point out again, is that the scenarios are definitions of workloads. They are not actual tests. Cray has an implementation of them. We believe that they scale pretty well. But the key part of this from the perspective of the DARPA HPCS program is that what's important to storage is the scalability of it. And Lustre does really, really well with certain types of workloads. As we know, sequential workloads we look great. Random, not so great. But those are the things we should be looking at. It's not just a single number, it's looking at how the file system scales, how our storage solution scales, identifying the bottlenecks and trying to wipe those away. So, furthermore, this Lustre talk, we did our test on Lustre, but if you've got other parallel file systems you want to investigate, these tests will work on those. We've played with them a little bit on Panasys. And then the source of the code is up there. It's our HPCS-IO at .cray.com. Please take a look, give them a try. If you've got any comments, we have an engineer who's monitoring the SourceForge website, and we'll be happy to include any fixes that you guys make or suggestions for improving the code. We'd be happy to take care of that. And that's it. Thank you. There's the fine print. Is everybody else who helped on this program? We had quite a team that was helping us move this through. A team at Oak Ridge, and then a number of people at Cray that are getting the test done. And that's it. Thank you.
Questions for John Carrier? Rich Brookner, ladies and gentlemen. Sark, you got a mic? No mic. Oh, Nikita's head.
It's coming.
Oh, there we go.
John, unrelated to your presentation, Cray just announced that they're going to sell their interconnect hardware to Intel, and it has something to do with Cascade interconnect hardware. Are you involved with that? You know anything about that?
I'm here right now. I'm not at the or the conference that you'll notice that all the Cray people left. They heard about it. I didn't.
Yeah. Okay.
How's that for an answer? Good. Over there. Hold it. He's got the mic. Rich recording everything.
So the 14 test that DARPA came and was very vague about, did we get feedback from what Cray came back to them and put up on SourceForge and said, yes, this does meet what DARPA
Yes.
was expecting?
Yeah. So when we engaged with them on this, there were members of the mission partner community who had said that Cray, don't do this. We're going to get the test for you. And we waited for actually 2 years before we finally gave up and said, okay, we're going to do them ourselves. So at that point, we engaged DARPA, said, if we're going to do this, we want to make sure that we're doing exactly what you want and that we've got your blessing with how the tests are done. So for that, they engaged Henry Newman of Instrumental, who wrote the document. Henry reviewed the code, reviewed our process. He took information back to the mission partners, and they did the review. I don't know if they went as far as a code review, but they saw what we were doing. The problem, to be fair, though, is that when Henry collected this, is Henry here? It's like 4 years ago? So was it 4 years ago or 5 years ago? Okay. Well, no, that's when the project started, but when did you actually first publish a document? Okay, well, that makes me feel really old. So Henry's saying is that this got started in 7 years ago. At that time, what they did is they went to all the mission partners and they collected what their workloads were, and then Henry defined them and went and reviewed them with all the mission partners. Everybody agreed that that's what they wanted. By the time we did this, many of the mission partners had left. And so there was a limited number of people that were actually engaged in looking at what we were doing at that. Just to be honest in where it all is. But yes, whoever's there, they did look at it and they knew that we were doing. And so the document, Henry and I re-edited it to make sure that the code we have actually matches the descriptions of the workloads that are in the document now. And a lot of it was just fixing some inconsistencies with the wording.
All right.
Great, thank you.
John Carrier.